Good afternoon, everyone. I'm Huang, Associate Professor for Social Sciences, and welcome to the Illinois Tech Social Sciences Great Problems, Great Minds seminar series. So for this seminar series, you can submit questions during the webinar by typing in the chat box. We will open the floor to the questions at the end. Today's speaker, Dr. Zhang, is a professor in the Department of Civil and Environmental Engineering at the University of South Florida. She leads the Smart Urban Mobility Lab and serves as the director of the National Institute for Congestion Reduction, a U.S. Department of Transportation FAST Actor National University Transportation Center. She is also the program director of advanced air mobility at the Center for Urban Transportation Research at USF. Dr. Zhang develops mathematically programming and solution algorithms, simulation tools, econometrics, and statistical models in machine learning, deep learning methods for obtaining innovative solutions for more efficient, resilient, and sustainable multimodal transportation systems. Her recent efforts focus on emerging services and technologies in transportation, including advanced air mobility and automated, connected, electrified and shared transportation. She has published scholarly articles on these topics in top journals such as the Journal of Air Transport Management, Transportation Research, Part C, Emerging Technologies, and Sustainable Cities and Society. Her research has been funded by the National Science Foundation, the U.S. Department of Transportation, the Federal Aviation Administration, the Department of Education, the Transportation Research Board, the Florida Department of Transportation, the City of Temple, and the City of St. Petersburg. She holds PhD and master degrees in civil and environmental engineering from the University of California, Berkeley, and a bachelor degree in transportation engineering from Southeast University of China. It's a pleasure to welcome Professor Zhang.
Thank you very much, Dr. Huang. Thank you for the introduction. And also it's my pleasure to be here with everybody and participate in this Great Problems, Great Minds seminar series. So if I may, I will advance my slides. So today I want to share with everybody about some research that we have done in the field of sustainable air mobility. So Dr. Huang has given a very extensive introduction. I'm leading the Smart Urban Mobility at the USF, and our lab is a part of another Center of Excellence for Aviation Operations Research sponsored by FAA. So here you can see this is a consortium of the university, and we just started a new research program called Advanced Air Mobility, which I'll mention a little more later. So the research areas of some lab actually could be summarized with this chart. When I was at UC Berkeley, I was trained to apply operations research tool and econometrics modeling in air transportation, specifically in air traffic management. And after I joined the USF in 2008, I got really interested in the application of shared economy in transportation. So from there, I started research in the shared mobility, including like a shared micromobility, bike sharing, e-scooter sharing, as well as a shared automated vehicle. And recently, we have conducted work on innovative aviation, including how to utilize the unmanned aerial vehicles to support the transportation system, both for the ground traffic monitoring and incident detection, as well as from the air side how integrates that into the airport operations. And also one major area that we're currently working is advanced air mobility, which use the vertical takeoff landing vehicles to provide the services to transporting passengers or cargoes by utilizing the low altitude airspace in urban area for the regional mobility, as well as serve those rural areas that lack of the air mobility services. So when I put it all together, we call it adaptive multimodal transition system. So we try to bridge the ground and air and to have future 3D transition systems that incorporate different transition modes, as well as using the different space to accommodate the needs and operations. So Dr. Huang just mentioned our research actually have a diversified sponsorship from government agencies at federal level, state level, as well as the industry partners. So probably the audience are not very familiar with aviation, and aviation is one important transition mode. Although the passengers that are transporting are not with a significant large percentage, but it's unreplaceable mode when we consider long distance or cross-continental travel. And in that sense, the commercial aircraft is very energy intensive. And because of that, it actually brings a lot of the negative environmental impacts. One is the greenhouse gas emission. So it's about 2 to 3% of global emissions actually came from aviation sector. The percentage-wise is not significant, but the decarbonization of that, which means find the replaceable energy to replace the jet fuel, is very difficult. And also a lot of the emissions actually occurred during the high altitude and also cannot be absorbed by other methods. So that's why it's a significant driver of the climate change. And also the aircraft's operations on the ground will generate the air pollutants like nitrogen oxide, etc., and affect the local air quality, because the engine of the aircraft are designed for high speed operation. When they are operated at ground at low speed, actually it's very, very fuel inefficient. And because of that, they emit more air pollutants than what was supposed to when engines are used. And another big pollutant is the noise. So the noise coming from the commercial aircraft, from the aircraft engine, actually will disrupt the local communities. And that disruption will lead to like sleep disturbances, stress, and other adverse health effects. Now, of course, when we consider locations where we have to do the de-icing before the aircraft can go to the runway to take off, or when we consider runoff from airports, the aviation sector also brings the water pollution. And another important environmental impact is the ozone depletion. So the emission at the high altitude could contribute to the depletion of the ozone layer and cause the problems to the health and as well as to the environment. So here just a kind of recent study on the carbon dioxide emissions from aviation. We can see it increase along the time because of the growth of the operations. And the percentage-wise, it goes from about 1% in 1960 now to about 3%. And as I mentioned, although the carbon dioxide emissions are about 2 to 3%, but the the climate change effect is about 4 to 6% according to the study. And FAA, as government agencies in charge of the aviation, have some net zero sustainability target. So by 2050, they want the aviation sector to become a net zero system. How can we do that? According to FAA's document, they are looking ahead and looking into like new aircraft technologies and the operational improvement or using the sustainable air fuel. So our study will relate to these different countermeasures and to see how we can help to reduce this environmental impacts of the aviation sectors. Now, one method of reducing the environmental impacts is try to improve the operation. And for improving the operation, actually, it's very challenging and with very high capital investment, and it takes really, really long time. So starting from 2005, FAA had a 20 years plan to modernize the national airspace system, and they take actions in different aspects. For example, to improve the communication, instead of relying on the oral communication between the air traffic controllers and the pilots, they develop data link, which means you can use the text message to communicate the very, very critical and important information. And also navigation and civilian system. So go from the ground-based radar system to the satellite-based GPS system. That will help improve the accuracy of the civilian system. Another one, of course, is automation, because when the density of the aircraft in one small area increase, it will be a lot of burden to the air traffic controllers and restricted by the cognitive levels of the air traffic controllers, then the number of aircraft that could be handled in that particular airspace would be constrained. So with more automation, it actually will assist the air traffic controllers to handle more and handle those much easier. Another thing is about the weather products, is to consolidate different products from the weather agencies and then provide better and more accurate information to the cockpit as well as to the operation centers of the airlines. And another area is the non-traditional NAS operations, which I elaborate a little bit. And advanced air mobility actually is a part of the non-traditional NAS operations. So, so as I mentioned, for example, go from the conventional ground-based radar system to the performance-based, we can see the trajectory of the aircraft could be much smoother and would help shorten the travel distance and travel time of the flights. So now I think everybody probably has flown the aircraft before, and you probably be quite familiar with the phases of a flight. So if we look at this illustration, the phases of flight at the airport go from the pushback, from the gate to the ramp area, and to the active movement area, and to the runway. And then for that part, what we call it is taxiing. So we have aircraft taxiing between the ramp area and the runway end. And from the runway, the aircraft will take off and the cruise and the descent and the final approach, land at the destination airport. And then they will also taxi in to the gate from the end of the runway. So the study have shown that, of course, we can rely on these new technologies. We can make the trajectory of the flight more smooth and more direct, and to shorten the travel time and save on the jet fuel. But besides that, it's really hard to, if we're still using jet fuel, it's really hard for us to reduce the consumption furthermore. However, on the ground, when we look into the taxi out, taxi in at the airport, we do find we can use some other technologies to help to reduce the fuel consumptions and the corresponding environmental impacts. So this is what we could observe at some of the airports. They do have a line of the aircraft waiting to leave to take off from the runway. And when we look at the different airports, here listed the top 12 US airports with the worst outbound taxiing delay. So we can see the New York, the average taxi time is almost 30 minutes. And in worst hours, which is about in the evening peak hour, the average time could goes to 32 minutes. And when we look at the airport and consider the distance from the gate to the end of runway, the impeded time, which means the time without a delay, probably is only about 7 minutes or 8 minutes. So we do observe quite a lot of taxiing delay at the airport, especially the taxiing out phase, because usually the taxiing in, which the aircraft come from the runway end to the gate, they get priorities to get to the gate faster, while the air traffic controllers will push the departure flight back and let them wait a little bit more. So conventionally, the pushback actually are carried by these type of tractors, and it needs the manually hook up between the tractor and also the nose scale of the aircraft. And once they pushed it to the end of the edge of the ramp, then the aircraft will turn their engine on. Maybe half the engine on. If they have 2 engines, they turn 1 engine on. If they have 4, they turn 2 on. And then the aircraft will move with the engine, give the engine on and go to the end of the runway. So as I mentioned earlier, these engines are designed for high-speed operation. When it is used on the ground for low-speed taxiing, the efficiency of the fuel consumption is really low, and also it emit excessive air pollutant emissions. So what we can do, we can look into these alternative aircraft taxiing systems. For example, this TaxBot system, which use like hybrid diesel and electricity, and also it could be automatically hooked with the nose scale without the human being. And they also have much significant power, can pull the aircraft from the gate to the end of the runway. And another method is that we can install what we call the wheel tuck system or EGTS system in the aircraft. And so there's a motor either on the nose scale or on the main gale, and then it's connected with the cockpit and powered by the auxiliary power system in the aircraft. And that part, the APU, actually is designed differently, that for the needs when the aircraft needs the lighting or the air conditioning. So if you use the power from APU, it will consume much less jet fuel and will lead to much less air pollutant emissions. So we call the TaxBot is external system, and on board is the internal system. And what we had done is we looked into these different alternative aircraft taxiing systems and understand their main features, their pros and the cons. And from there, we also conduct the environmental impact analysis of these different types of alternative aircraft taxiing systems. So we look into 4 different scenarios. One is look into conventional, and second one is just to put the single engine on. The third scenario is use the external system, and the fourth scenario is onboard system. So I will not go into much details. So we basically obtain the data from many different resources and fuse the data into a database, which will support our study. We also made some assumptions, which are pretty reasonable. One is that the alternative system can achieve current taxiing speed. So the taxiing speed on the ground at the airport is about 15 to 20 miles per hour. And those taxi bot or the wheel tuck or EGTS actually could achieve that. And also we assume the external system will not cause additional delay. I would say this is not sometimes under certain circumstances, this may not be true, because if we use the external system, the wheel tug, then we may need the auxiliary road to let them go back to the ramp area so that they can pull another aircraft. And if not, it may cause a little bit additional traffic in the aircraft taxiing system. And another one is that we assume that emissions from engine warm-up phase and the conventional APUs are all the same in all scenarios. Because of that, we do not include those into our calculation. So the worst taxing out delay that we have observed in the history happened in 2007. I think back that time, it was at the one peak air traffic demand in the history, because in 2008, we encountered the recession. So back at the time, the average taxi out time in JFK, New York, is 37 minutes, and many of others are more than 20 minutes. So, those taxing delays leads to many economic loss, as well as the air pollutant emissions and environmental impacts. So here are some results. We looked into the fuel burn, because fuel burn is directly related to the carbon dioxide emissions. So we do not have a figure specifically on the carbon dioxide emission. But from the figure, we can compare the fuel consumptions of the different scenarios, and for different air pollutant emissions, the hydrocarbon, the carbon monoxide, the nitrogen oxides, etc. And then further down, we normalize these numbers and try to compare them in a better way. So we can see that we can easily compare the effects of the different alternative aircraft taxing systems to the different environmental impacts. And the conclusion is that, if we could use alternative aircraft taxing system, it will bring the significant reduction in the fuel burn on the ground and also the emissions. And while we compare the different systems, we see that the onboard shows the best performance in the emission reduction. But the scenario 3 actually shows the least fuel burn. So what happened is, although the APU is designed for lower intensity usage, but still APU actually is more energy intensive than the taxi bot that designed for pulling the aircraft on the ground. However, the scenario 3, which is using the taxi bot, the automated taxi bot, shows the increase of the nitrogen oxide emissions compared to other scenarios. So the results actually show us the trade-offs in fuel and emissions among these different technologies. However, when we look into the general indicator by consolidate the greenhouse gas emissions and air pollutant, think about how to mitigate and alleviate them, then the scenario 4 actually shows the best potential of reducing the local environmental impacts. So that leads to our conclusion, and I think we also suggested there should be more future work before implementing those alternative taxing systems at the airports in the US. So that is one sample study and related to sustainable air mobility. And recall what we have discussed before is that we could do something to improve the operations in the aviation sector. Meanwhile, we could also look into the innovative aircraft technologies. So now there are a lot of discussion about, and also the efforts on developing the electricity aircraft. And for the normal aircraft, unfortunately for powered by electricity, those aircraft could not be too big. So a lot of the studies, researchers' efforts are putting on the regional jet, which is, go from maybe 35 seats to 70 or 80 seats. So those type of commercial aircraft is potentially to be powered by electricity. And meanwhile, on the other side, people are asking for alternatives, alternative air mobility, which can help them avoid the congestion on the ground, could provide them more convenient, transportation mode between the cities, and also to some rural areas that does not have the air mobilities currently. So that's why starting from 2007, NASA actually proposed this terminology called urban air mobility. So that focus on use the electricity or hydrogen-powered vertical takeoff landing vehicles to transport passengers and cargo. And transporting passengers in the urban field, actually, urban area is not a new thing. We already seen the helicopters transporting passengers from the downtown to the airport, or provide, services to the tourism. But the new concept, urban air mobility, are enabled by the innovations in electricity-powered aircraft manufacturing, as well as the information technologies and the satellite-based navigation and surveillance system achieved during the next gen, the modernization of national airspace system. So compare the advanced air mobility with the commercial aviation. The advanced air mobility actually could serve the short-haul markets, for example, 50 miles, 100 miles, 150 miles markets, which lack of the commercial air service now. And also the advanced air mobility, those eVTOLs maybe can accommodate like 4 to 6 passengers. So they could, and also the cost of doing so is much less. The unit cost of doing so is much less than use those large commercial aircraft. So it's possible to provide more frequent services. And when they compare with the helicopter, these are the distributed propulsion systems powered by electricity. So it's much less noisy and more reliable, which means if one of the fans here lose the power or malfunctioned, then the aircraft actually can still run. And this kind of design requires less space and electricity power, so it's more environment friendly. When it compares to ground transportation, it can provide a faster mode and also help avoid the roadway congestion. Although there are a lot of benefits, of course, to realize this new mode, there are lots of challenges. And when we think about challenges, we first could look into the potential applications of this new mode. So here are the market category, and here are the market types. So it could be used for first response, air commute, air shuttle, etc., etc. And from the researcher's perspective, we usually focus on the passenger AM, for example, air commuter or air shuttle. So air shuttle, one important air shuttle is the airport shuttle between the residential area or downtown area to the airport. And the air commute could be on demand, could be shared services provided to the travelers. So at the early stage, the AM could be one of the regional air mobility. For example, in Florida, we do not have a lot of intercity commercial air service. So possibly we could create this kind of network and connect the major cities in Florida and provide more frequent services. Otherwise, by going from one city to the other, the driving time is between 3 hours to 5 hours. So some people may think this is still far away, but actually it's not, because the OEMs has been working on this for a long time to develop a different prototype and testing them. And the two of the companies in the US actually filed the certification requests to FAA. One of them is called the Juby Aviation. So this is a model that they filed the certification request. And other one is the Archer. And their designs are different. So if you're interested, you can read this description to understand their designs. And the what we heard from FAA is the certification may be approved probably in late 2024 or early 2025. And meanwhile, in other countries, there are certification process going on. And also there are bilateral agreement between different countries with the US. So if the aircraft is certified in other countries, then with limited additional steps, they could be certified in the US as well. So given this process, we can foresee that the first generation of the AM will arrive probably in 2025. So the FAA actually envision evolutionary stage. They talk about, okay, initially they be treated as just a general aviation. Only when they get into the constrained airspace, controlled airspace, for example, around the busy airport, then they have to follow the air traffic controller's guidance. Otherwise, they can fly as the same general aviation right now. And as a midterm operation, and eventually in a mature state, we will see hundreds or even thousands of simultaneous operations in the airspace. So that leads to challenges how to make the operations safe. There are lots of efforts from NASA and from the academia, from the OEMs to contribute to the safety operations of AM. So actually, NASA has this roadmap going from 2025 to 2024. So they will focus on the data and the resilience analysis, on the strategic conflict management, tactical conflict management, and also to see how the weather, low altitude weather product could be generated and used by this safety management. So there are lots of things going on, lots of efforts, and try, to, when we talk about 2024 is a mature state when we have hundreds or even thousands simultaneous operation in the air, we can use the automated air traffic management system to ensure the safety of the AM operation. So at USF, our smart urban mobility actually started the research in AM about 6-7 years ago. And about at the end of last year and the beginning of this year, we consolidated expertise from our smart urban mobility, as well as the professors from computer science, from industry and management system engineering, from mechanical engineering, from electrical engineering, from business schools, and we create this AAM research program at the USF. So we focus on 3 areas. One is the passenger AM, which I will elaborate a little bit more. And the one is the cargo AM, and also another area is UAS applications in transportation. All right, so one sample project I want to share with the audience today quickly is the integrates the network design and the demand estimation for the shared and on-demand UAM. So you can imagine, I know a lot of you probably have used the bike sharing, right? You go to a station or you go where the bike is, and you unlock the bike and ride the bike and return it somewhere, either station or somewhere close to the building, and then you get to your final destination, the building. And the thing about this shared AM is that you could go from your origin using the ground transportation and get to the vertiport. And at the vertiport, you will be assigned to an eVTOL. And that eVTOL will take off and take you and maybe some other shared passengers to the destination vertiport. And at the destination vertiport, you will get off the eVTOL and use the ground transportation to get to your final destination. So this is a process of this multimodal passenger AAM. And in this process, one important ground infrastructure is the vertiport, right? So this vertiport is a location where the eVTOL could take off and land, and the passengers could get on board or embark from the eVTOL. And also because electricity power, so you need to have a charging facility to make sure that the eVTOL could continuously operate. So, but at the same time, that vertiport would be much simpler. It does not have very fancy like gate area, like a lounge or a restaurant or stores. Instead, it need to facilitate the expedited process of passengers going through and, to connect the ground and air transportation mode. So when we look into the literature, we found some gaps. I will not go into the details, but if I go to the next slide, is that our model is integrated model, which means we can capture both the network design as well as the individual passengers' mode choice. And we know that mode choice actually will affected by where the vertiport is located. If it's located close to your home or your workplace, then your access time is much shorter. And vice versa, if it's far away, then it's hard to access. So how to access the vertiport will affect the people's mode choice. But the demand for people to convert from ground tram station to air tram station will affect the optimal locations of the vertiports. So our model actually captured the interactions of these two parts. And I will not go into the details. Here is about how we identify the candidate vertiport locations. We look into the land use types. We look into if there's enough space according to the FAA's vertiport design guidance. And we use the single allocation hub and spoke problem modeling by adding a set of constraints to show the mode choice. What we call extended single allocation hub and spoke problem. We solve this problem by using some solution algorithms, and it will give us the optimal vertiport location. So I would have to excuse me because I found out the slides that I'm using is not the most current one. So I'm gonna close it and I'll see if I had the slides updated from the box folder. Sorry about that. Okay, I think this is the right version. All right, so I was talking about the mathematical modeling. Just to make sure. Yes. Okay, so I was talking about mathematical modeling. So from there, we also use assumed pricing scheme, which from the Uber Elevator or other OEMs. And with all this information, we have the paper where you can refer to. With all this information, what we could gain from this research is the optimal locations of vertiports and also how much passengers would divert from the ground tram station to this multimodal AM. And also we can find out what pairs of vertiports that each passengers will go through, which is called passenger allocation to the vertiports. We also can find out the best access and egress translation mode of the passengers for going to the vertiports and leaving the vertiports to their final destination. And with that, we can estimate the save the travel time and also the reduce the system generalize the cost of the system. For example, we apply that to the case study of the Tampa Bay region. We also conducted some sensitivity analysis, and from the sensitivity analysis, we can know that what is the optimal number of vertiports to serve the region. When we say the optimal number is that there's a turning point where we add more vertiports, we actually will not attract more or much more passengers from the ground tram station. So the turning point is considered as kind of give us the optimum number of vertiports. And we also can know the impacts of the pricing schemes and the impacts of the intermodal efficiency. So the case study of the Tampa Bay region, after we run the mathematical modeling by using the solution algorithm, we can find, from the 100 vertiport candidates, we can identify 30 optimal locations. And then here shows how many passengers actually will be served at those 30 vertiports. And from there, we can also find out the travel time saving distribution. So in our case study, most of the diverted passengers can save about 30 minutes of their travel time. And in terms of the times in the different phases of trips, we see that, about 25, I would say 17% of the time are used for accessing the vertiports, and about averagely 30% time is en route, and another 20-ish% is egress from the vertiports. So this is just to summarize this particular study, and you can find the paper from our lab webpage, and there are lots more details there about this study. So at USF, besides this integrated network design demand estimation, we actually are working on different modules. For example, enhance the regional demand modeling by incorporating the AAM, and also look into automate the energy efficient AAM flight planning, so it can help us to better estimate the en route travel time of the eVTOLs. And with that, and together with the scenario generator, we actually could do regional mobility impact analysis. We can do the energy and environmental impact analysis, as well as the equity impact analysis. I understand that the audience of this presentation are from social science. So Dr. Huang mentioned that probably the audience are pretty much interested in learning more about equity related research. So for the equity, we actually done some previous study, try to understand or try to develop a method to help us to evaluate the equity for the applications of emerging technologies and the business models. So one study that we have done is looking into the bike sharing and try to analyze and understand if the different populations gain the benefits from this new transition mode. So bike sharing became really popular in the US and across the country in last decade, starting from about 12 years ago. And then now, we have millions and millions of trips every day across the world. But the question is, do the benefits from the bike sharing evenly distributed across the different population groups? So when you look at the headlines of those articles in the medians, it shows that they are concerned about, and they're not sure about the answers. So a lot of people saying that the bike share has the equity problems, and the benefits actually are concentrated on certain groups. And a lot of research show that, the white populations, the men, actually those are the large percentage users of the bike sharing. So our study tried to look into literature and understand the state of the art of the research approach for analyzing the equity for the emerging technologies and business models. And after reviewing those literature, we found out there are a couple of gaps. So one gap is they focus on aggregated data. And when we use aggregate data, we actually lose lots of the individual heterogeneity. And that will lead to, some results cannot be used effectively for us to come up with some countermeasures to improve the equity. And another gap is that existing methods focus on accessibility to the bike sharing facilities, but they do not consider the trip and also the tour of the users, and do not consider how will help them to get to their final destination. So the multimodal characteristics actually is missing in the existing literature. And recognizing these two gaps, we propose our own methods to fill in these gaps. So our solution is a disaggregated approach. And this approach is we look into locations on the bike sharing infrastructure, and we get the data about individual daily travel itineraries, as well as their social demographic information. And then we develop a method for us to calculate the tool-based individual accessibility. And with that metric, we can calculate the equity, both the horizontal equity and also the vertical equity of these emerging translation modes. So how can we do that? Let's look at this individual travel itinerary. So there's one person go from the home to the shop, maybe in the morning, to get the coffee before this person goes to the workplace. And then during the day, this person also goes to the restaurant to have lunch. And after work, they go to the supermarket to do grocery shopping before this person goes back to home. So we know this daily travel itinerary. And meanwhile, if it's a station-based bike sharing system, we know the station locations of this system, like indicates with this blue dots and numbered from 1 to 7. Now, if we look at the single trip, for example, if we look at the trip from the workplace to the restaurant, knowing the locations of the bike sharing stations, we see that this particular person can go to different nearby bicycle stations and get the bicycle and take the bicycle to their destination stations and then leave the bike there and goes to the restaurant. So looking at this, we actually we can analyze the accessibility for each step. So the step that I showed earlier could be measured as the distance decay, which means when the distance is longer, then the accessibility is lower, and vice versa. So we use the method from the existing literature to calculate this function. And then with this function, we can get the accessibility, which is a number from 0 to 1. So higher the number means better accessibility. So comparably, the station 3 and 4, the station 3 actually is easier to be accessed by this particular person. And then at the destination part, the station 6 is easier to access. And then what we can do is we can calculate this entire trip. We do the multiplication of this accessibility for the different modes, walking, biking, and walking, and we get 0.336. And for this particular tool of this person, we can actually calculate the accessibility for each of the trip segments. And once we get that, we can calculate the tool-based accessibility. And for the tool-based accessibility, we separate them into 2 subtours. So the first tool is a circle going from the home to shop to the workplace and then to the grocery shopping and back to home. And another subtool is go from the workplace to the restaurant and going back. And for these tools, we can calculate the accessibility, tool-based accessibility. And then the individual accessibility is the summation of the accessibility of these 2 subtools divided by 2. And in this case is 0.28. So now given the individual data, we actually can calculate, each individual's accessibility given one day of their tool, one day of their activities. And then after that, we actually borrowed some method from the existing literature, and we calculate the Lorenz curve, and to access the accessibility, access the equity of the horizontal equity of the bike sharing. And so for this horizontal equity, we actually carried out at individual level, parcel level, and the TAZ level. And given limited time, I will not give the details. And we actually apply the methods to the case study of City of Tampa bike sharing program. So if you refer to the reference I mentioned earlier, you can find more details. And the conclusion is that the bike sharing program in the city of Tampa is not equitable, which means the benefits are not evenly distributed among the individuals in the population, either within the geographic space or among different social demographic groups. So in our paper, we also emphasize the necessity of using the tool-based analysis, because if you only look at the single trip, then it does not capture the interactions of the different activities from the same individual. So we believe that incorporating this aggregate level data, it actually could improve our analysis of the equity while we're embracing these new technologies and the emerging transition modes. And we also did work sponsored by FHWA, which is looking into the equity analysis of the automated vehicles. So I'll stop here. In this presentation, I touched on some studies to make our air transportation more sustainable, to provide the new technologies to support the urban air mobility and also advanced air mobility. And also I presented a research approach to analyze the equity, horizontal and vertical equity of emerging transition mode. And this method actually could be used for analyzing the automated vehicle, the shared automated vehicle, as well as the advanced air mobility that we're currently working on. So here's some in the website. If you would like to obtain more information, you can go to our website. There's a publications. There's also short kind of introductions of the projects that we have either accomplished or that we're working on. So thank you very much, and thank you for your time. I welcome any questions and comments.
Thank Professor Zhang gave a very interesting talk about the sustainable air mobility regarding the the aircraft tax delay scenarios analysis, and also the environmental impact analysis of the advanced air mobility. And also includes some like equity of bike sharing system. So I found it first interesting is that you showing the framework of your current research. So how actually, so we know like currently we use the ground automobile systems is related to the shared economy. But how the because I saw your the framework of the air transportation also related to the shared economy. So could you explain how actually that are related?
Sure. Yeah, so as I mentioned, the advanced air mobility that we're currently working on at the early stage or along the progress or along the development stage, it will be shared service. So you can consider like you or your colleague can go together to the vertiport and then be assigned to the same eVTOL for getting to another city to attend a conference. So it's a shared service. It will be operated by private sector, but actually it provides a shared transportation mode to the users.
Okay, I see. So then the other actually is in the slides. So probably it's better I just stop you when you talk, but I did not. So you mentioned that for the tax delay systems, actually there is assumption is external systems. Actually, it's so could you explain what that external systems means?
Oh, okay. Let me give you a little bit more. I'm going to share my screen again.
Yeah.
Okay, so
there's the assumption is the I think you list some assumptions. Yeah.
Assumptions.
So the external system will not cause additional delay. So what's these external systems?
So the external system and onboard system are relevant to
Okay.
the aircraft itself. So the external system is more this like a taxi bot outside the aircraft, and it will be connected with the aircraft and pull it and to the end of the runway. So we call it external system. And this onboard system is you add a motor on the aircraft itself, and the pilot in the cockpit actually could control the system while they are taxiing out or taxiing in. And that equipment or motor actually use the power from the auxiliary power system, usually installed in the back of the aircraft. So that one can turn on and generates the electricity for the lighting and for the air conditioning of the aircraft. So instead of, when aircraft is parked at the gate and we still have the lighting and air conditioning on, right? The power does not coming from the engines. It came from the auxiliary power system in the aircraft. And also it could come from the outlet from the terminal building, but not all aircraft are using outlet from the terminal building. So they're using the APU to support the air conditioning and the lighting. And the onboard system is we can add the motor on the aircraft, and that is powered by the APU. So by doing this, we can reduce the jet fuel consumption and also reduce the emissions. So that is what in the assumption we talk about external system. So think about, if you have that kind of system, pull the aircraft to the end of the runway, they need to go back to the ramp area and serve another aircraft. So previously in the taxiing system, we may only have the aircraft running over. But now, besides the aircraft, we will also have these type of vehicles running in the taxiway system. So if the taxiway system is not sufficient, it may cause additional delay. But in our study, we assume that will not happen, which means we will do a good ground traffic management to make sure that the running of the external system will not cause additional delay in the taxiway system.
I see. So, which means that you can make sure they are not negatively affected by the outside of onboard system.
Yeah, we assume that the aircraft operation will not be affected by the additional taxi bot in the taxiway network. Yeah.
Okay. I see. So, and also for your findings, your finding is about the environmental impact analysis for these 4 scenarios. So, do you also consider some like the economic cost related to this scenario?
In our study, we didn't consider economic perspective, but we worked on one ACRP project. ACRP means Aircraft Cooperative Research Program, sponsored by Transportation Research Board, by collaborating with industry partners. So if you refer to that report, we actually looked into the costs of the different alternative aircraft taxiing systems.
I see. So what's the result from that based on these 4 scenarios? So which means that the most benefit environmental scenarios will also has the good better economic cost, or how actually they are integrate with the economic cost based on these 4 scenarios?
Actually, in that report, we didn't integrate them together. We had a lot of discussion on, we're not talking about economic aspects of this environmental impact. We're more talking about, how this alternative aircraft taxing system could be implemented at the airport if it's external system, or what is the cost for the airlines to add those on their aircraft. So we more look into the capital investment of these alternative systems.
So which means to see which scenarios can have more capital investment, and that's from that report you mentioned.
Yes, that's right.
Okay, I see. So then should be related to like the cost, because usually like the less cost should have more investment, right?
Sorry, can you ask that question again?
So, I mean, should be related to the capital investment, should be related to the cost. When have the less cost, then can attract more investment. Should.
Yeah, of course. So we need to compare the cost and the benefit, right? So look into cost to benefit ratio, and then to see which type of system actually is more attractive to the users. This is a little bit more complicated because when we look at the external system, it's possibly that the airport will invest into that. So like when we talk about the conventional pushback, these tractors are actually property of the airport. And for the airlines, when they use it, they will pay the airlines for using this kind of service. So if it's external system, then the airport can possibly invest into this and let the different airlines use these tractors. Versus when we look at the onboard system, then the airlines, they have to invest to retrofit their aircraft so that they can have these onboard systems. So our study is looking into this, but it's really hard to compare because they're kind of, orange and apple. So it's really dependent on, maybe some busy airport, they got a lot of landing fee and a passenger facility charge from the airlines, and then they have more funding, possibly can help them invest into this external system. Versus for some airlines, if they have more financial capabilities and they want to take advantage of these onboard systems, then they can invest into this. So it's really hard to compare the entire airport industry using invest into external systems and the entire airline industry invest into the onboard systems.
I see. There's some like a cost sharing there. Okay. Just see if we have any questions from the audience. So then the next question is about the advanced air mobility. I found it's interesting.
I heard some voice from other attendees. Maybe they have questions.
Yeah.
Oh, okay. Saber,
Yeah.
can you ask question? Yes.
Yeah, so I saw you showed 2 model airplanes that have electricity and use electricity. What's the status on those planes? Are they being built? Have they been built? Are they flying?
You're talking about advanced air mobility, the eVTOLs?
Yeah.
Are you talking about this?
Yep, those.
Yeah, these have already been built by Joby Aviation and Archer. So when they file the certification, they need to have already built the prototypes and also prove they have capabilities of manufacturing these in a scale. So there have been testing across the world of different eVTOLs. You can see that they tested in Dubai, in Singapore, in China, Australia, and in Texas, state of Texas. Yeah.
Okay, and then, as this technology gets improved and regulations get put in place, the purpose is to slowly shift over to these electricity powered airplanes, right? To help with CO2 emissions. Is that the goal?
Okay, so advanced air mobility only talk about the small eVTOL, small electric vertical takeoff landing vehicles. And it cannot replace the commercial large aircraft. So for the large commercial aircraft, researchers are talking about using hydrogen fuel cell as the energy. And for like when we talk about 250 seat capacity aircraft, when we look into like the jet, regional jet, maybe under 100 seat capacity, then it's possible they could be converted into the electricity aircraft. The advanced air mobility that I'm talking here is more like a flying vehicle or called an air taxi. So they can accommodate like 4 to 6 passengers. And at the early stage, there could be like one pilot on board. And for the current commercial aviation, we do have 2 pilots in the cockpit to ensure the safety of the aircraft. But for this advanced ability to reduce the cost, we will have single piloted aircraft, but with on the ground, there's some operators assist the pilot in the aircraft during the operation. So from FAA perspective, they need to certify several new things. One is the single piloted. Is that safe enough when supported by the ground operator? Second is electricity powered propulsion system. And the third is the distributed propulsion system. Because the distributed one, then the control system in the aircraft is pretty challenging to build, to be built and to be operated. So basically, those are the new field of the certification, aircraft certification from FAA's perspective. That's why they are also learning and come out with the criteria, and then they will evaluate if the Joby Aviation and Archer, the aircraft that they are building, will meet the criteria. So that is the certification going through FAA right now.
Okay, and then one last question. So for cargo use for these kind of smaller planes, I would think that Amazon and Uber and the cargo companies would be really interested in this kind of technology. What have you heard in that sector? Is it maybe too expensive right now for them, or are they partnering with you to create this kind of technology faster and better?
Yes, they are already using some of these technologies. So when the Amazon is such a big company, when they go from one distribution center to another distribution center, they currently use those airports, right? And they have large aircraft carry the goods to the airport and then use the trucks going to the distribution centers. But this vertical takeoff landing, they could operate directly from their distribution center without going through other infrastructure system. And Amazon is very interested in expanding that. So one of our study actually received Amazon Research Award, and that is to automatically generate the pre-departure flight planning for the high density operations. And also advanced mobility covers the small drone delivery as well. So Amazon and other big chains like Walmart or others, they're already using the technologies to assist to their delivery.
Well, very interesting. Thank you.
Thank you.
So for this the advanced air mobility, this aircraft certification. So you mentioned I think you also mentioned that is the vertiport location selection. So which means I wonder if for using this current eVTOL, this vehicles, so it will be used the existing infrastructure, can use the existing infrastructure, or actually need to build the new infrastructure.
It's possible to use existing general aviation and helipads, because lots of our general aviation, actually, they're economically not sustainable. So they also are, their operation, the density is pretty low. The frequency is pretty low. So yes, so there are lots of discussion on how to utilize the underused general aviation airports as the vertiport to accommodate this new mode. Now, the challenge would be how to set up the charging stations so that the vehicles, the eVTOLs, could be charged at those general aviation airports. Yes, so also people are considering, like, I think it's here. Are considering using the rooftop of the parking garages. For example, there's one company called Frovio. Frovio, they actually had a contract to build 20 sustainable vertiports in Spain. And then another company called the Skyports. And the Skyports, they have partnered to explore the biometric and the vertiport technologies. And they also set up agreement with the parking company called Park 25 in Japan, and talk about how to retrofit the rooftop of the parking garages to the vertiports. Yes, so there are a lot of the existing infrastructure could possibly be used. But we are waiting, when I say we, the stakeholders are waiting for the guideline from FAA and also some policies and legislation. Because FAA actually sent out a guideline before, and I think it lacks of understanding of the future needs of the vertiports. So they actually revoked that guideline. And hopefully in the airport has office called, the FAA has an office called Airport Office. So they are working very closely with the UAS office and try to develop a new guideline for the vertiport construction and operation.
I see. So which means we need a new policy to guide this emerging technology implementations.
Yeah, of course. Because currently when we look at the helipads, we do have the guideline about how to construct the helipads, how much space it's needed. But the future eVTOLs, they are different from the helicopter. So if we follow the helicopters or helipads guideline, it will require much more space and make the physical footprint of the vertiports way too much than needed.
Because for the eVTOL currently, this one is smaller. The size is smaller than helicopter. Oh, okay, I see.
Yeah.
And also you mentioned in your site selection, you mentioned there's a coordinated vertiport. How that's different from the new selected vertiport?
Oh, what I said was the candidates.
Coordinated. Yeah, that map, the site location that you're showing the different colors. Some is the destination. I think is next slide. Next.
Previous slide or next slide?
Showing yeah, this one. The hub small spoke problem?
Okay, so this figure shows
Oh,
origin.
candidate. Sorry. Yeah. It's yeah. That's
Candidate reports.
oh,
Yeah.
okay.
So
That makes sense.
Right.
Yeah.
So the squares shows the candidate vertiports. Those are the rooftops of the high-rise buildings used
Okay.
commercially used in downtown area or open space in suburb or rural area that potentially could be a vertiport. So by analyzing the 3D map, we identified, in Tampa Bay region, we identified 100 these type of candidate vertiports. And then the dots here are showing the origin destination of the individual trips. And then what the problem that we are solving is, given all this information and also the parameters, how we can determine the optimum locations of the vertiports that we want to put in the region. For example, it's a p-median problem. If we say we want to put a 10, then from the 100, we can find the best 10. If we say we want to put a 20, then running the model, we can find the best locations for 20 vertiports in the region.
I see.
Yeah.
And also the other question is, in terms of you mentioned the safety, the certificate actually is regarding for the safety. So, and also it seems it's mentioned it's consistent with the Europe standard, or so. So I'm wondering, in terms of these safety issues, what's your thought about the public perception or acceptance of this new eVTOL or technologies use in terms of people more concerned is like safety or the price, because you also mentioned the price things.
You're right. There are lots of concerns from the public when this new mode come in, right? And I didn't show actually from the NASA's FAA perspective, there are challenges in different fields. And the one challenge is the community engagement and acceptance, community awareness, engagement, and acceptance. So there are lots of concerns from the community, like the visual pollution. Like people do not want to see a lot of the aircraft flying nearby, right? And also, although it is electricity powered, the engine itself or the propeller itself is quiet, but when we consider the turbulence with the air, it may not as quiet as we expected or as we hoped or as the OEMs claimed. So yes, so the noise, the visual disturbance, and also is a safety. Now, safety, of course, should be controlled by FAA. So FAA, the certification process is to ensure the safe operations of the vehicles or the flying, the aircraft. So we have been doing this all the time, right? That the large commercial aircraft, after they were manufactured, they will go through the certification process of FAA. So, but on the other side, there's one interesting survey shows that a lot of people, they want to have the vertiport in certain distance away from their community, but they do not want the vertiport in or on their community. So it's like, I like to have some vertiports maybe 2 miles, 3 miles away from our subdivision or our community, but not right here.
Yes, so, that makes sense. It's yes. Like I want the convenience, but I don't want it disturbed.
That's right. Exactly. Yeah.
Okay. Yeah.
So that could lead to some equity issues. It's a similar thing as, okay, when we build the highways, maybe they go through this low income community because the land is cheaper. And on the other side is when highway is built, the land along the highways may become cheaper because of the noise and the pollution from the highway. And the developer will buy those lands and build a low cost housing, right? So where the vertiport will be located, we do not know, if that will deteriorate the transportation inequity, or if we can use some way to if there's some income for the cities from the vertiport construction operation, then if they use that back to enhance and improve the transportation for that particular community, maybe we can go from the vicious cycle to a more kind of better cycle, like to let the community benefit from this new transition mode, and that can help us to alleviate the transportation inequity that we had before.
Yeah, that's exactly. And when I send you an email about kind of interested in this equity issues, all for this eVTOL eVTOL vehicles. So then, in terms you said, what's the current these vertiport locations? Usually they located it's close to the airport, or like use the rooftop, or what's their locations is like similar with the airport, or it's actually different?
Okay, in Florida, the Floraville actually has already have agreement with a Palm Beach airport, so they're gonna lease some land on the airport and build 2 vertiports. Because as I mentioned in the previous use case, the airport shuttle is one of the future market, to transport people from downtown, from some concentrated residential area to the airport, right? That's a kind of express way for people to get to the airport and catch their flights. So yes, so airport will potentially be a location for the vertiports. And the Tampa International Airport already included that into their master plan. So they did a study, look at several potential locations where they can put the vertiports, and they analyzed why these cannot be and these 2 could be, and they included into the master plan. And the airport's master plan need to be approved by FAA, so they already submit that to the FAA. And a lot of those companies like Floraville or Skyports, they are continuously looking for the opportunities or candidate sites of the future vertiports. We know that for this kind of emerging transition mode, there has to be a network, which means you need to have vertiport here and there, and eventually become a network. Only by having that, you can encourage the development of the AM system, right? So for Floraville and the Skyports, those are construction companies. They have lots of capital, lots of cash at hand. So what they are doing now is look for potential locations and either convert them into vertiports or construct new vertiports.
I see. So for your last part, the bike sharing, I just wondering, what's the spatial scales you use? Because you mentioned that you use the actually is not individual level data. So then what the spatial scale you use?
Okay, so in Tampa Bay region, we actually are District 7 of Florida DOT. And we do have activity-based demand modeling. And from there, we actually could simulate and running the simulation and get the individual trip for the entire day. So the information that we used is that, in our region, for each individual, where do they go? And where do they go? And also what transportation mode they currently use. So we do have that simulated activity-based demand of the people in our Tampa Bay region. And our model is, to utilize that data and then look into the bike sharing program in downtown Tampa.
I see. So which means you did use this the individual level data.
Yeah. So our contribution is we did this aggregated approach.
Okay. I see. Yeah, that's impressive for using this individual activities data. Thank you so much. Yeah, to give this very interesting, and also I think it's touched different perspective. So not only just I think both from the technological perspective and the environmental and also equity issues. So thank you so much for giving this great talk. So usually we give applause to the speakers at the end. So then, which is